Okay, so we have our last lecture topic for the year. So that means next week we have three core classes. Each class can be a working day. And obviously I'll be here to help people out with whatever they need. And so the last topic is formal methods. And as a generic term, what is a formal method? What is a formal method?
A rigorous mathematical method for reasoning over some system.
Yeah. And providing, so which means since it's rigorous, you're providing definitions and you're providing, and since you said mathematical, you're providing definitions in a mathematical context. And what we mean by that is there are non-ambiguous definitions for every entity in the system, and there are non-ambiguous rules for how those entities get manipulated or updated or modified. And so that's what every computational system is. And the rationale for providing formal methods for anything, formal methods have some protagonists in software development. We talked about formal verification validation techniques earlier in the semester a little bit. The reason for doing those things is by putting things into a mathematical framework, you end up with provable discussions about properties of systems, as opposed to opinions about properties of systems, or beliefs about properties of systems, or statistically likely descriptions. You can develop provable systems. That's the benefit. The downside is, well, not necessarily a downside. The thing that scares people away is sometimes they become notationally dense. But generally, you can get around that. Sometimes they're not very notationally dense, and even if they are, if people are developing tools for people to use, then the tools hide that complexity from the user. So, to start out the discussion, we won't talk about simulation in general. We'll talk about something called a finite state machine. A finite state machine is a simple model of computation that is presented to any undergraduate who's taking a computer science curriculum, and generally a software engineering curriculum too. And the finite state machine is composed simply of nodes and then edges from one node to another, and then a description of what symbol the machine is processing that directs at what edge to go to, which edge to take. So that was a very poor definition. It's a set of nodes, it's a set of edges, and it's also a set of input symbols that are allowed for the machine. So the machine starts out in a particular node, it processes a single symbol on an input, and each edge is dedicated to a single input in a deterministic machine, and that puts us into a new node, which is a new state. And then we process another symbol, and we go to another state. So the idea is, if I do a simple machine like this, I've got state 0, I've got state 1, and my language is composed of the symbols A and B. And so if I'm in Q0, I start out in Q0. If I get an A, I stay there. If I get a B, I go to Q1. And if I get a B, I stay in Q1. If I get an A, I go back to Q0. This is a completely random machine, but it gives you the idea of I've got states, Q0 and Q1. I've got edges. This is a deterministic machine because for every possible state symbol pairing, I know exactly what I have to do. I have exactly one choice, one option. So if I'm in Q0 and I get an A, I know what to do. If I get a B, I know what to do. So this is a deterministic finite state machine. There are non-deterministic versions of this, but we don't need to talk about that in the context of this. Why are these things useful? In and of itself, a finite state machine, strictly defined, is a not a very powerful computational tool. And the reason is that the finite state machine doesn't have any memory. And so without memory, you lose some capability. In a finite state machine, you always know where you are. You never know how you got there because you don't have any memory. However, the finite state machine is used as the basis for many computational systems. So, for example, in model-based verification and validation of software, they model the software system as a state machine, and then they provide transitions via the edges for every possible input that that state machine may experience. And the trick is you start out in your initial state, when you first power up the program, it shows up in some initial state. And then you try to find a path via legal inputs to some bad state. The classic example is traffic lights. Traffic lights should be like on an intersection that goes north-south and east-west, it should be green north-south and red east-west, or green east-west and red north-south, right? It should never be all green for everybody at any given time. That's a bad state. So you can model the software that's controlling the traffic light and start out with, it doesn't matter which, green and red for, red east-west, let's say, green north-south, and then model all the inputs that traffic system can see if you can ever get to the all green state. That's how they're used. They're used, we talked about this in verification, validation of simulation systems, models and simulations in the same way. You use the same kind of techniques. And so they're used as a basis for that. They're also used as a basis for agent behavior. And since we're talking about agent-based simulations a lot in this class, it's relevant. So there is I forget the name of the companies, SARC or something like that. They created this very expensive simulation for the Army that was a small unit tactical trainer. So it's individual tanks, individual soldiers, that kind of thing. And when they wanted to say, oh, we're going to move a platoon of tanks, 4 tanks, from point A to point B, it turns out that movement has a certain phases. And so they start out in a deployed position like a diamond shape. And then from the diamond shape, they have to transition into column. And then from column, they go to where they want to go. Then once they're in there where they want to be, they go back into a diamond shape. Well, how would you model that? You model that as state changes. We're in the state where we are forming up the column. Now we're in the state where we are in the column mode. And so we can travel. Now we're in the state where we're at our destination and we have to reform the diamond. So this is a fairly common way, actually, for people to get sequential agent behavior in a model. There's a branch of behavior representation that never really caught on, called context-based representation, and that was done by a guy named Avellino, what's his last name? A UCF professor, and he did context-based reasoning, and it was basically the same idea. I'm in this context. Here's the problem with AI. If you try to do everything at once, it overloads the system, right? So the AI has to filter out in a rich system where you have a lot of behaviors. It has to filter out what's useful and what's not. Just like you do. Like you know how to go grocery shopping. You don't worry about that now because you're sitting in a classroom, right? That's filtered out of your awareness. So in the context of sitting in a classroom, you only have certain rules that you worry about. And that's what he did. He said, oh, okay, I can do context-based reasoning. I am in this context. I have this set of rules. But I can transition to a new context with a new set of rules. And I can transition to a new context with another set of rules. And we have to define what those transitions are. It's a finite state machine at heart, dressed up with the extra rules. So finite state machines in and of themselves, as formally defined, bare bones, are a very simple computational model. But you will find them everywhere. It is normal if you're defining your software or software hardware system to lay out the design using various diagrams. Some of the diagrams are basically state-based. I think you mentioned, Alex, you wanted to do a state diagram at some point for your software, right? So right. So it's just things are inherently state-based, so they work. All right. So a while ago, this guy Bernard P. Ziegler, University of Arizona, I believe, came up with this something he calls the Devs formalism. Oh, have you?
Yeah.
Oh, really? He's still around then? No, there you go. Oh, I owe you one too. So, yeah, he made his whole career off of devs, and devs is huge. There are devs conferences. I mean, this paradigm took off. And so I don't know exactly when he started it, but it's been a while, yeah. So here's a book. This is a whole book. This paper that I'm giving you is a whole book. You see, it's 147 pages, and it's about the devs paradigm. This was from 2003, but devs had already been developed before then. I'm going to say somewhere in the mid 90s, I think, yeah. And what devs does, and again, people who have these things, like Avellino developed context-based reasoning, which was a very fancy finite state machine. He always got upset if you ever mentioned that it was like a finite state machine. Right? So I'm not sure how much Ziegler ties into the fact that this is a dressed-up finite state machine, but it is. It's a very well-developed state-based system. Let's put it that way. And the state-based system is that you have a model, and the model is in a certain state, and then when the model gets changed, it moves to a new state. And one of the clever things that he did is, how does the model change state in a simulation? Because the original model, as you see, had an external entity that was feeding in symbols. So there's an external stimulus. But a simulation, once you say go, doesn't have an external stimulus. So how do you go from state to state? And he put a timing function in. So basically, you're in this state, and if something happens to change the state, you'll change the state. But otherwise, the timing function will time out, and that can change your state, or that can modify the variables or the attributes in such a way that you'll change the state. And this technique, this notion of devs, is very successful. So we had a professor here that left. When did she leave? Were you here with Jeff here?
She looks like right
It was
before.
2000
It
and
was like.
yeah, that's right. 2021, somewhere around there. Yep.
Right before.
Yeah. And she had done a lot of work in devs. And when she taught this class, she taught it using the devs formalism. So, and like I said, you can go online and you can find there are annual conferences just devoted to this, how to do modeling and simulation using devs.
Yeah, only that I had known back then that I was working with the Dr. Z.
Yeah, I know, right? The same thing. I worked with Kenneth DeYoung in the early 2000s. And then I found out later, he's like the founder of genetic algorithms, right? He's the first guy that did the seminal paper. So. Was he using devs? Yeah, everything was just, yeah. So you can explain this better than I can, because I've never modeled in devs. I've read the books. So he's got, if you look at the definition of model, it's composed of S, X, Y, Dn, the external lambda, and Ca, and the X is the set of inputs, the Y is the set of outputs, S is the set of states, and the deltas, the delta internal and external, are the time advance functions that are either due to internal or external stimuli or the passage of time. The actual output behavior, output function lambda, that's a function, not the, right? So you have a set of outputs, Y, but how do you know which one to pick at any given time? You need functions for that, right? So you have a set of functions, that's what the lambda is. And then what are we saying TA is? That's the time advance function. Okay. So it's again, you can define it bare bones like that. And then from there, you can get multiple textbooks to read, right? To get fancier with it. And in the textbook, if you scroll through the chapters, you can imagine this simple model. You have to start to worry about, okay, that's great, but how do I actually use it? How do I actually model a simulation? Now go into the other topics that we've talked about. We've talked about parallel and distributed simulations. What the heck do I do with that, right? He's got a chapter about that in the book. How do you handle parallel and distributed simulations? Think about how the time advance function gets messed up as soon as you enter the distributed world or the parallel world. By definition, you have chaotic behavior between the different processors. Think about how the time advance function gets screwed up with a multi-resolution simulation, right? Where you have different time domains at the higher level and lower level of granularity. So all of these things can get much more complicated. This is just a basic overview. And a reminder that if you're fishing around for a way to formalize your models, DEVS is probably the way to go because it's the number one, as far as I know, system. There are other formal modeling systems out there, but for modeling and simulation, this is probably the best way to go. The other techniques would be things like lambda calculus, way too mathy for most people. And there's something called Z, language called Z, which is a formal logic language. And it is so notationally dense that you poke your eyes out. So again, DEVS is a common, lots of resources on how to use it. And you can actually model directly from a DEVS model, a DEVS-based model. You can create a simulation directly. Okay, so time advance function, that's going to be something that's normal in every simulation. So we've talked about the idea of a tick. If you have a simulation, remember you've got features, which are the items of interest in the real world, and then you've got attributes, which are the representation of those features in your model, and then you're going to have attribute values. And then you need some mechanism that will update those values. So you need an update function, but you need to know when and how that update function gets called. So the standard way to do it in a time-based system is to just loop through and check every entity. Hey, are you updating? Are you updating? Are you updating? And each entity will look at its surroundings and see if there needs to be some kind of an update. Right. So for FCM, did the edge dump me a new value or not, right? It's that simple. So that's a typical time advance function in a time-based simulation. We've also talked about schedule-based, right, event-based scheduling, where you don't do time linearly. You just say, hey, the next event in this simulation, I'm going to schedule it for this time, this simulated time period. And then the next event comes at this simulated time period. And you mentioned queuing models a minute ago, Alex. A lot of queuing models are that way because they're like, hey, if no customer shows up to the bank, I'm not going to waste all my computations, cycling through the ticks where nothing happens. I'm going to go event to event to event rather than just modeling every 1 second or whatever the time frame is. Hello.
Sorry.
Okay. So yeah, we're talking about adding more material to the course. Maybe going more in depth into DEVS would be useful for this course. Maybe. And then I came up with the simulation dependence graph as part of my dissertation. It did not take off, right? DEVS is the standard. This model did not take off, but it mirrored very well what high-level architecture did for modeling and simulation, and that's why what I liked about it. So I've got some notes here about simulation dependence graph, and here's the basis and the rationale for that. most of you have taken a programming course, and in that programming course, you had to do a flow diagram before you wrote, right? That's often how they do that, right? You do a flow diagram, and you start out at the top, and then you come to an if statement, and if true, go this way, if false, go that way. That's called a control flow diagram because you're following the flow of the control structure of the program, right? So we say, oh, okay, true, false, do this stuff, come back together, do some more stuff, right? You're following control, and it's control flow. You can also do data flow. And in data flow, and you may have done this without it being called data flow. Have you ever had to, as in part of an assignment or even part of your troubleshooting, you look at where a data value gets assigned and you trace through the program that variable, when did it get modified and what did it get modified to, where you're tracing that by hand or tracing that in some fashion? That's called data flow. How do the data values get set and then assigned later in the program? Okay, so we have control flow and data flow. But we also have something called dependence. And what control dependence differs from control flow is if I do control flow and I've got lines 1, 2, 3, 4, 5, 6, and let's say line 4 is an if then else. Okay, so in control flow, I'm going to go 1, 2, 3, 4, and then depending on whether this is true or false, I'm going to go 5, 6, 9, 10, or I'm going to go 1, 2, 3, 4, 7, 8, 9, 10. That's flow. But what about dependence? You ask yourself this question. Hey, look at line 6. How do I know if line 6 is going to be executed or not? Where does that occur in the program? Line 4, right? Right here is the decision. If this is true, 5 and 6 will be executed. That's where the decision is made. If this is false, 7 and 8 will be executed. So we call that dependence. Line 6 is dependent, control dependent upon line 4. Rather than flow, we're saying, what does it depend on? And if I start the program with an imaginary line 0, then I'll say, okay, line 1 is dependent upon line 0 because it's always going to happen no matter what, right? As soon as you say start, it's going to happen. And line 2 is dependent upon starting the program, and line 3 and line 4 are all dependent upon that. But line 5 is dependent upon line 4, and line 6 is dependent on line 4. How about 7? Also 4. Because if 4 is false, 7 gets executed. If 4 is false, 8 gets executed. But that's where the decision is made. So this is the difference between flow and dependence. Okay? Now, what if we said this? X equals something, Y equals something, and this if function is a function of X. Now we talk about where did X get defined and where did X get used? And so X was defined here and used here. So line 4, since it uses the value of X that came from line 1, is dependent upon 1 from a data standpoint. So in the original stuff you guys talked about, you did control flow and you did data flow. Now we're going to talk about control dependence and data dependence. Why the distinction? Here's why. What does your compiler do to your program? You write all this lovely code in Python or Java or whatever, and then you hand it to the compiler. And what does it do? Or C? This is particularly true for compiled, not interpreted programs. What's the compiler do? Just in rough terms, I don't need details. Any thoughts? Been a while since somebody mentioned this to you. Your compiler takes your program and rips it to shreds. Because what's the job of the compiler? To go from high level to machine language, right, to executable code. And what's the other half of that? To make the machine code efficient, right? We talk about program optimizations. So the compiler will take your code and rip it apart and then put it back together in such a way that hopefully the program can execute efficiently. And a lot of this efficiency comes from like memory fetches. So we want to make sure that the memory, the data that's in the RAM memory gets put into the cache memory in a timely fashion so that it can jump right into the processing unit without any delays. So what does that mean? It means that your processor or the compiler will take your program, rip it apart, and start to reorder the sequence of things. If you think you did things in a top-down manner, and that's logically how you're thinking about your program, be aware that the compiler will rip it apart and change the order. But there are rules, and the rules are simple. The compiler can screw around with control flow all it wants. It can mess around with data flow all it wants. It cannot change the control dependence. It cannot change the data dependence. So as long as control and data dependence are respected, then the compiler can do whatever it wants. Yeah.
So then is there a way to see like how it changes the code? You say if you printed like a simple like if-else statement, like I did, could you get the compiler like a second third-party source to print out how it changes?
What you can do is instead of that, because looking down at the machine level code is very difficult for a human. You could reverse, there are ways to reverse engineer machine code back into high level code, and you could see if there are differences. But easier than that, there are well-known transformations that compilers do. And so you can just say, oh, I suspect this has been applied, right? You can also, if you're compiling, I'm sure you can do it using Eclipse and VS Tools and all those things. I'm sure you can do this. I know you can do it if you're compiling from a command line. You can specify the degree of aggressiveness you want the compiler to use when trying to find optimizations. Right. And once you just specify a degree of aggressiveness, if you go to the documentation for the compiler, they may tell you, oh, we're going to try to do this optimization, this one, this one, this one. There's about a score or so of just standardized, well-known optimizations. I mean, I'm going to give you a really easy one. Okay. There's no reason why this should be done inside the loop, because you're going to do it a bunch of times, but you're always going to get 10, right? So what do? The optimizer will put it here. So it's only done once instead of n times. I mean, that's a stupid simple optimization. Some of them are also when a system is storing matrices, you've got a 2D matrix. So here's your 2D matrix, right? It's got a bunch of rows. So it's n by m, rows and columns. How's that stored in memory? Any thoughts?
Is it list or arrays?
This is an array, a pure array, an honest to gosh array.
So then would it just take up the whole block of memory and just have array next to array next to array? Like back to back to back?
Back to back to back, right. So it says, here's row 1, and it's n columns big, so there's n spaces there. And then it does row 2, also n spaces. And then it does row 3, also n spaces. So instead of doing it, we visualize it as a two-dimensional thing. It's a vector, it's a one-dimensional thing. But here's the question. Is it going to do the rows, or is it going to do the columns? So it might do column 1 with n spaces because that's this column. And then it might do column 2 instead of row 2 with n spaces, and then column 3. So the question is, which is it?
Or does it?
Depends on, of course it depends. Just like, the big endian, little endian argument, right? Different operating systems will do it differently. So what does your compiler do? It knows, quote, knows, it's been designed for a specific operating system. So if you're in an operating system where you're being stored this way, it will go through the loop sequence in such a way that this works. In other words, your loops will go through each row and then come down to the next row, go through that row, come down to the next row. But if you're in this system, the loop, and it doesn't matter how you write it, the compiler will reorient it so it goes down down a column, comes back, goes down a column, comes back, goes down a column. So, these loops, for I equal 1 to n do, for j equals 1 to n do, those double loops, it might flip it and put the j on the outside and the I on the inside. Because in one of them, you're going row first, and the other way, you're going column first. So it has to know. Now, why is it doing that? It's doing that because you're taking big chunks of memory and putting it into the cache so it's readily available to the processor. And if you do it wrong, you're going to you need that element, that element, that element, and you can't take that as a big chunk and put it into the cache. So instead, you reorganize it and take that big chunk and put it in your cache. That's just, again, these are standard compiler optimizations. And there's about 20-ish of them. Any computation that can be done ahead of time, statically, will be done ahead of time. So you know how sometimes you'll put in, they tell you like, oh, for a variable, for a constant variable, it's good programming practice to not put the value in, but to make a variable, set that variable, and then never change it, right? You make like a static variable or something like that. Well, guess what the compiler does? It doesn't keep that variable. It actually performs the computation. And however much of the computation it can roll through the program during compilation, it will do that. So it doesn't have to do it during execution. Okay. Anyway, the bottom line is with compilation, you can do anything you want as long as you respect the dependencies. So I started thinking while I was writing my dissertation, which was about developing a dependent system for Java language. And I was working at, IST, Institute for Simulation and Training. So I was starting to think, oh, okay, along the same lines should we model models and simulations as dependence structures? And so, when you're doing your dissertation, you have to be very formal, right? So it's very formal, right? So a feature is a representation of the measurable aspect of the real world. An attribute is the representation of that feature in the model, which really means the attribute is a range of values. Now think about data typing. What is a good definition for a data type? A good definition for a data type. By the way, this always works. I've never seen this. I think I may have seen it one time, but I came up with this myself, and I've never seen it published anywhere except maybe one time. What is a data type? Here's what a data type really is. It's a range of values and associated operations that you are allowed to perform on those values. That's what it is. So when you say I have an int, what are you saying? Here's my range of values, and here's what you can do with it. plus, minus, multiplication. Not so much division, right? Right? If you say I have a float, here's my range of values, here's what you can do with it. Right? The same thing with a character or a string. So an attribute's a range of values. I is a single value integer union with, we're going to use I for integers, R for rationals. That intersection with that funny little symbol, that thing is called bottom. If you have you ever had in your program not a number show up? Something like that, or right, not a number, can't calculate, whatever. Some systems crash, some just report back not a number. That's what that bottom means. It's a bad value. It's a value outside of the system, and you can't do calculations with that bad value. So then you've got your range of values, and if you have the empty set, you've got an attribute that has no members at all, and so on and so forth. So we're basically just defining everything I can about how you're going to deal with an attribute. And in a formal system, you have to be that complete. Remember, you have to provide a rule, a definition for every possible situation, and a rule for what happens in every possible situation. So formal systems, this is why people run away from formal systems, because they don't want to go to that level of detail. But once you've defined it all, life is pretty good. So then we can say, oh, an attribute vector, remember a vector is nothing but a one-dimensional array. So an attribute vector is just an ordered sequence of attributes, also known as a tuple. Attribute value vector is all of those attributes, the values of each attribute, right? So the distinction between the two is, if I have an attribute vector, here's what I'm telling you. It's basically like saying I have x1, x2, x3, x4, x5. Here I'm just using A to be consistent with the previous notation. And down here with the value, I'm saying, oh, the value of A1 at this time is alpha 1. Right? There's a distinction between saying I have a variable x and x equals 10. Make sense? So then I say, okay, attribute 2 is at alpha 2. So when you want to talk about the state of a simulation or the state of a model, you say, oh, the model is defined by this attribute vector, right? These are the features of interest that we have for the model. And at this point in time, what is its state? These values. Take a snapshot. Those are the values. If one of those values changes, we're in a new state. This is why we started out with state-based systems. Okay. If these are my attributes in the model, and these are the values that those attributes can take on at any point in time, by the way, the value of alpha 1, let's say, is going to range from some lower value to some higher value, and that's what we're defining up in here, right? The ranges of values. So, if the model is going to be entered into a simulation where we have updates, we need to have a way to do an update function, and that's what this is, the update function. So for each one of these attributes, I'm going to have an update function. By the way, this fits again really well into an object-oriented design. The correlation between models and objects is pretty strong. All right, so that's that definition. Then I can define a model as a set of these features with the associated attributes and update functions. And because I use the word set, by the way, if you use the word set ever, use it intentionally. Because as soon as you use the word set, you get a lot of stuff for free. Like, I'm saying, hey, since I'm using the word set, I can compose models together through set union. I got that for free. And I can decompose models by subtraction, by set difference. So when you use the word set, you get all the set functions for free. You also get the nice duality of you're either in the set, out of the set, so you get logic for free. All right, all this is leading up to There's my model. So now I've got my model is a set of the features that I'm interested in, the attributes that represent them, and the update function. Then I've got another feature, attribute, update. If I put them all together, I've got a model. If I keep composing those things, I get model composition. And if I do enough of those, I'm going to have a simulation. And then I can talk about interesting things like, completeness. Do I have, contained within my model, do I have an update function for every attribute? If I don't, I can't run the simulation. I can also talk about ambiguity. Do I have more than one update function for each attribute? So from there, we have the basic definitions of models and simulation. And then from there, I can go to the simulation dependence graph. And the way I'm defining that, now that I have models and simulations defined, is I can say, oh, okay, it's a node E, F, E, 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 C, E, 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 C. Those are my edges. My node set is my a single attribute with its update function, and a tag that designates whether it's going to be pushing or pulling. In other words, is it spitting out values or does it need to request values? And then the E of F is the flow dependence edges. So we talked about that before. It's a control, a data dependence edge. So if I need to know other attribute values in order for my update function to work, I need to get that. I'm dependent upon other nodes. And then my EC, instead of doing control dependence, we're doing control sequencing. So I can do that through a list of edges. And then the entity, let's talk about it. I think that's an E. The entity edges are just saying, look, all of these attributes, because the model is at the attribute level. How do I know if I'm part of the same entity in the simulation? So for example, with an automobile, the automobile might have 5 attributes. And if I put an automobile in the simulation, all 5 attributes show up at the same time. And if I take that automobile out, all 5 attributes have to come out. So all this is saying is, hey, are you part of the same entity? In other words, do you show up at the same time as a group, or do you come up? So that's the definition of the simulation graph. And then from there, you can actually construct a simulation and run it using this model, or you can start to do provability type stuff with the model. Now, this, the whole world ignored this, right? So this is like, you'll find this in one place. But my one true contribution here is ants on a log. So I needed an example in my dissertation, and I'm trying to think what's the simplest simulation you can construct. And I came up with this. Think about it. What is the simulation? What is the simplest simulation you can construct? What do you need? What are the bare bones things that you need in a simulation? Agent-based simulation. You need an agent, and then you need an environment. That's it. Ants on a log. Simplest environment is a one-dimensional environment, right? The ant can go from left to right, from right to left on the log. That's it. That's a simple environment. And then you have a single ant, it just can go back and forth, right? There's your simulation. But from there, you get remarkably complex, remarkably fast. You can have multiple ants. They bump into each other, they turn around, they go back, right? Or they push each other along the edge. Then you can start to develop logs with branching, right? So I was very pleased with that because it's simple, one-dimensional, right? But it gives me everything I need to know for a complete simulation. And then I can describe how the simulation dependence graph fits that. So the main exercise of this is not that you're ever going to use a simulation dependence graph. It's a nice model, but devs is the way to go. Take this though as an example of when we talk about formal systems, what level of detail we're talking about. Every entity needs to be defined. Every possible situation needs to be defined. Every update function needs to be defined. Now, you'll notice I'm not saying in the case of the where am I at? There we go. In the case of each attribute, and I'm saying there's an update function. I'm not saying what it is. It could be anything. It depends entirely on the simulation, right? You've got an update function that basically just shoves the value from a node out into an edge. And then that edge has an update function where it just chunks the values through the cube, right? That's your update function. You've got, we're up in the air about this, but it looks like we could create maybe two different update functions and then have part of your node description is the choice of are you going to use update function A or update function B. Right. So we don't have to define what the update functions are because they're so unique. But in a formal system, you acknowledge that they exist. And you have to define what it does. It takes in attributes and it spits out generally a single new attribute, a single attribute value. I recommend, unfortunately, there's not a lot of opportunities in the commercial world to work with formalisms. And unfortunately, there's not enough time in a 4-year program to work with formalisms. However, if you go into grad school, I recommend that you steer yourself this way if other people aren't already steering you this way. And here's where I'm a pretty big formal systems person. I like them. And here's what I like about them. You guys have already experienced how hard it is to actually produce working product, working software, if you don't have a good design. You may have experienced it in this class, you may have experienced it in another class, but that's the hard part. The better your design, the easier the easier and quicker the code production is. Formalisms are, in my opinion, a great way for you to think about your design. You know, I used to teach the Organization of Programming Languages course, and I said, who in this class has actually invented a language? Nobody would raise their hand. Who in this class has written a program? Everybody raised their hand. Guess what? You wrote a program, you invented a language. Because all a language is a set of allowable strings, and once you define your program, you're defining what strings are allowable. So be aware, if you're aware of that, and you can use the formalism tools that come with languages, Backus-Naur form grammars, finite state machines, stack machines, that kind of thing, then it helps you it gives you a tool to clarify your thinking about your design. And that is the hard part. That's always the hard part, is getting down to getting your design to a fine degree where producing the code is, again, that should be the boring part. And again, we're human, and students do this a lot. It's I've got this all figured out, and I've got this all figured out. I haven't figured this out yet, but when I'm doing the code, I'll figure that part out, right? That's a normal thing that we say. And that, when you find yourself saying that, you should actually fight that, right? Because what you're saying is, I did the easy stuff. This part's hard, so I'm not going to worry about it yet. Right? But the hard part is the part you need to solve before you do the code. Okay, so anyway, there's some ideas of formalism. That Ziegler book, it's an honest to gosh book. I don't think I'm violating copyright by posting it. It was found online as a right. Once things go online, they tend to be public domain, so I think we're good from an ethical standpoint here. You know, you can read through that book. Use it as a real resource. So, Alex, you worked with Ziegler. What was the SBIR for?
It was an AFWorks. So we were trying to, he works for a company called RT Sync now, he's like their chief science officer.
Okay.
And they're developing a simulation environment for the Air Force Research Lab that basically uses devs and allows you to like model different processes, and what they're interested in is modeling like drone processes. And so we were working on that for trying to like sell this product to the AFRL. So we were developing like using actual